In this video, we will discuss 4 different methods of describing vector direction. Let's use the vector shown to describe the 4 different ways we can talk about direction. The first way is we can talk about the direction as being measured from due east, measuring from the positive x-axis. So looking at this 60-degree reference angle, that means from the positive x-axis, from due east, we are looking at 120 degrees. So that's it. The first way of describing vector direction would just be to call it 120 degrees. And we got that from the positive x-axis. The second method is to say how far the vector is, how many degrees it is, from west or north or east or south. For example, this vector is 60 degrees above west, or we could say 60 degrees north of west. So that's another way we could describe direction. 60 degrees north of west. Now this angle up here on the other side of the vector is 30 degrees. So we could say that this vector is 30 degrees to the left of north, but instead of saying left, we would say the vector is 30 degrees west of north. So 30 degrees west of north. So this is the second way of describing vector direction. Now the third way of describing vector direction is almost the same, but you'll notice that north and west will be reversed. For this method, imagine that you are telling someone where to look, but first you're going to tell them one of the 4 cardinal directions. You're going to first say, for example, start by looking west, okay? And in fact, this is how you would describe, instead of saying 60 degrees north of west, I'm going to convert that to this new method. So by this new method, you would start by saying, all right, look west. All right, there's me saying to look west. Now turn your head 60 degrees north. And there it is. This would be the way of describing the same direction. So instead of saying 60 degrees north of west, you say look west. Now turn your eyes 60 degrees north. So you're looking west, and then you move 60 degrees north, and then you're there. So of course, if we want to rewrite the next one, okay, so instead of starting looking west, imagine that you're giving someone directions, and you say, okay, start by looking north, and then you'll have to turn your eyes 30 degrees to the west, and then you're there. So this is the third method for describing direction. You can see how similar these two are, and it can be a little bit confusing because 60 degrees north of west is the same thing as west 60 degrees north. All right, the letters become reversed, so it can be confusing. But just one more time, in this method, the idea is the first letter is telling you where to look, and then how far to turn. So start by looking north. Now turn 30 degrees to the west. So look north and move 30 degrees west, and you're there. The fourth and final method for describing direction is called bearing. Now the different thing about bearing is that you are always measuring from north. So whereas when we just said 120 degrees, we were measuring from the positive x-axis. We were measuring from east. When you say bearing, you're going to be measuring from north. And you always have to move clockwise instead of counterclockwise like we did for the 120. We have to go the other way and measure from north. So for bearing, this vector direction would be like this. We're measuring from north and we're going all the way around like this. Okay, so notice so far I've gone 270 degrees. If I go 60 more degrees, that's going to be a total of 330 degrees. So another way of describing the direction of this vector would be to say bearing 330 degrees. Again, this bearing 330 degrees was measured clockwise from north. Side note, bearing always uses three numbers. So if you were going to talk about 45 degrees, you would say 045 degrees. Now, I went ahead and rewrote my notes to go along with the first method of direction to match the way I described bearing, so you can compare them easily. So bearing is measured clockwise from north, whereas a simple 120 degrees would be measured counterclockwise from east. Okay, problem number 1. We are supposed to use a ruler and a protractor to draw an arrow diagram where we're talking about a magnitude of 60 meters and a direction of north 45 degrees east. Okay, so we're talking about this method where we're supposed to start north and then rotate, and then rotate 45 degrees east. We're definitely going to need our axes, our north, south, east, and west, and also we're going to need a scale. So obviously I don't have space for meters on this paper, so let's let 1 centimeter equal 10 meters. So we have 60 meters, so that means I'm going to need 6 centimeters in length. Now I am zooming out so you can see my protractor, and I've got my ruler off to the side that I can use. The way I will use my ruler is I'm going to expand my protractor to make the radius be the size that I need. So I want 6 centimeters to represent 60 meters. So I'm going to enlarge this protractor until the radius is equal to 6 centimeters. Alright, so I think the easiest thing to do is to move the protractor so that the left corner of the protractor is at the left end of the ruler, and then I can just drag this corner. Now I'm keeping an eye at the middle of the protractor because I want that to be 6 centimeters. Okay, so just watch that middle line, watch me line it up, boom! Right now I have a protractor that has a radius of 6 centimeters. Now I'm going to bring my protractor back so I can measure my 45 degree angle. But you know what? I see my radius is going way out into the words and everything, so I think I'm going to shift this whole thing down. I can use the lasso tool to probably do this. Alright, I'm just going to move all of this down so I have more space. Okay, now north 45 degrees east means start at north and then rotate 45 degrees in the direction of east. So if I put my protractor right at the origin, then I can easily see where 45 degrees to the east is going to be. Okay, so 45 degrees is going to be right here in the middle. And also, because I made the radius of my protractor be 6, all I have to do is extend my vector to the edge of the protractor, and I am golden. Okay, I'm going to go ahead and make this pink and make it a little bigger. Okay, so now I should be able to move my protractor away, and there it is. Let's see, let me put a little extra mark in here to show that this was 45 degrees. Started north, moved 45 degrees east, drew my vector. Okay, for number 2, we need a bearing of 220 degrees, and then I'll worry about the 100 miles later. Now remember that bearing is measured clockwise from north. So if we were talking about a bearing of 220, we're talking about moving 220 degrees clockwise from north. So there's 90, there's 180. Okay, if I went all the way to here, that would be a bearing of 270. So that would be too far. So I know that we're talking about the third quadrant here. Okay, so we're talking about the third quadrant. This is supposed to be a bearing of 220 degrees. So it would be useful to know what the reference angle is. So look, if this is 220, bearing 220, and if this was 270, then that's a difference of 50. So that is the reference angle that we're dealing with, and that's what I'm going to use my protractor to create. Let's talk scale for a quick second. I would like to be able to use centimeters. I'm trying to represent 100 miles. So I think a scale of let 1 centimeter equal 20 miles would work. 20 goes into 100 5 times. Okay, so that means when I draw my vector in a moment, I want my vector to be 5 centimeters long. Each centimeter will represent 20 miles. 20 times 5 is 100. Okay, so with that in mind, I'm going to adjust my protractor so that it has a radius of 5 centimeters. So again, I'm going to grab my protractor. All right, I'm going to put it over here towards the left edge of my ruler, and then I'm going to drag it, and I'm looking for, I'm adjusting so that the center of the protractor is at 5. So right now you can see that the radius of my protractor is 5 centimeters. Now as I drag my protractor over, it's sitting here in the first and second quadrant. I need it down here in the third and fourth quadrant, so of course I can just rotate it. So under the draw menu, I've got rotate. Oh, you know what, I could probably flip it, but I want to rotate it. I'll rotate it 90 degrees, and then I'll rotate it another 90 degrees instead of flipping it. I think if I flipped it, all the numbers would be backwards. So now it's facing the way I need it to be, so I can just move it. I want a 50-degree reference angle. So I'm going to go ahead and draw my vector now. Okay, and using these numbers right here, here's my 50-degree reference angle, but I'm going to go ahead and stretch this vector out to the edge of my protractor because I have sized the protractor so that it has a radius of 5 centimeters. And there you go. So to complete the diagram, I'm going to go ahead and show that a bearing of 220 degrees was measured clockwise from north. Okay, bearing. So we have bearing 220 degrees diagrammed. Problem number 3. Caroline walks 45 degrees north of west for 1,000 feet and then walks 200 feet due north to go grocery shopping. How far and at what north of west quadrant bearing is Caroline from her apartment? Let's see. What did Caroline do? What did you do, Caroline? She walked 45 degrees north of west. So here's west. 45 degrees north of west would be about here. All right, so she did that for 1,000 feet. So there you go. Then she walks 200 feet due north. So I'm going to make another vector. 200 feet due north. That would be something like this. Now, we want to know how far and from what north of west quadrant bearing is Caroline from her apartment. So we are talking about the resultant vector from the beginning of her trip all the way to the end. I'm going to make this one green because it's the resultant vector. So it's the green vector that we want to know about. All right, the magnitude and the position. Now, in order to solve this problem and calculate the magnitude and direction of this resultant vector, we need to organize our work. We need to break down the first vector and the second vector into component form so we can add them up. Because the sum of these two vectors will give us the resultant vector that we want. So what we are given is magnitude and direction. So we have to start from that. So look at the first vector. We need the magnitude and the direction. We have to be a little bit careful here. The magnitude, of course, is 1,000, so we can safely write that down. Now, how about the direction theta? This 45 is not the direction that we need. We need the direction that would be measured from east. So if this reference angle is 45, if we measure from east all the way over counterclockwise to here, that is going to be 135 degrees. I got that from taking 180 minus 45. So when we talk about magnitude and direction, the direction is this 135 degrees. Now, what about the second vector? All right, this little 200-foot vector. Well, that 200 feet is the magnitude, so let's go and put that down. Now, how about the direction? When we talk about the direction, we have to imagine that the vector is in standard position, so we need to imagine that it's at the origin, like imagine that it's right here, and this is 0, 0. So this would be 90 degrees, would be the direction. So we have 200 is the magnitude, and 90 degrees is the direction. Now let's turn this magnitude and direction into component form for each vector. And the way we do that is that we are going to do r cosine theta for the horizontal component, and we will do r sine theta for the vertical component. And we're going to do that for both vectors, r cosine theta and then r sine theta. All right, this might be hard to fit because the numbers are so big. Okay, now in this case, maybe I'll better write this down here. R cosine theta, we're talking about 1,000 cosine 135. So you know what, I think I'll go just straight for the calculator. So R cosine theta is 1,000 cosine 135. That's my r cosine theta. Okay, so that gives me negative 707.1. See, what do I want to round to? Now, r sine theta, that's 1,000 sine 135. So 1,000 sine 135. All right, so the vertical component is 707.1. Okay, so that's component form. Now for the second vector, this is going to be a lot easier because, look, the horizontal component will be 0. I don't actually need to do r cosine theta. I mean, I could, but I don't need to because it's a vertical vector. There is no horizontal component. So the horizontal component will be 0. The vertical component, I don't need to do r sine theta actually, because the vertical component is the full 200. Okay, so now for the resultant vector, all I need to do is add the corresponding parts. So I think I'll change colors to green, all right, representing my resultant vector here. If I add negative 707.1 and 0, of course I'm just going to get negative 707.1. If I add 707.1 and 200, that's going to give me 907.1. So this is my resultant vector. Now, I need the magnitude and direction of this. All right, I have these rectangular coordinates. I have the component form. But to answer the question, I need to change this back into the form r and theta. I need the magnitude and the direction. So how do I do that? Well, I think it would be helpful to make a diagram out of this. So if we're talking about a vector that goes left and up, we are talking about the second quadrant. So check this out. And I mean, it's right that we knew it was in the second quadrant. So I'm sort of redrawing this diagram just with my resultant vector shown in a simple way. So here is my resultant vector that I'm trying to analyze. Okay, but now I'm going to break this down into the horizontal and vertical components. So it's left 707.1. So that means over here I have 707.1. All right, I don't really need to put the negative on it. I mean, I guess it doesn't hurt. And then it's up 907.1. So this vertical portion is my 907.1. So I can find this reference angle, which I will call R, using tangent. So what I can do is, I know that the tangent of R will equal 907.1 over 707.1. I'm ignoring the negative sign because I just want the positive value of R. So in that case, the value of R will equal the inverse tangent of 907.1 over 707.1. Okay, and I'm just going to put that in my calculator and see what that is. Okay, so I'm doing the inverse tangent of 907.1 over 707.1. So my angle is 52.1 degrees. Got to round up a little there. Okay, so that angle is 52.1 degrees. Now in the past, we have ignored this angle and just used it to find the measure of the angle all the way from east. And that's what we've been using for the direction. But for this problem, we're not going to do that because they actually are asking us to say 52.1 degrees north of west. That's the type of direction we're supposed to use. So this is actually the angle that we want, so we're good. All we need to find to be finished with this problem is the magnitude. So I'll just draw a line, and let's find the magnitude, and I can call it R for I often use R for the magnitude. But that's just going to be the square root of, and then I'm going to square each of these. So it's going to be the square root of negative 7, put that decimal in the wrong place, negative 707.1 squared plus 907.1 squared. All right, I just need to work this out. So my magnitude is going to equal, and I'm just going to punch this in the calculator. So here I've typed it in the calculator. Let's see what I get. 1150.1. So the final answer is that the magnitude is 1150.1 miles, and the direction is 52.1 degrees north of west. Hey guys, that's going to do it for this video. Go ahead and click over here to watch the next video, and click over here to subscribe. That way you'll get every new video delivered right to your home screen.